All right, can everybody see and hear?
Aye.
Good. All right, so we're done calculus. You guys have worked so hard. I'm so impressed. Thanks everybody for staying on track and getting that done. We're now on to vectors. Today we'll do our introduction lesson, and there's a short, I think pretty short practice to do, and then you'll have the rest of the day for working on your midterm. Hopefully ironing out your technology details. So today, the first couple of pages are just a lot of definitional stuff, not too hard. And then, actually, I don't think you'll find today too hard unless you find recalling the trig stuff hard, and I'll go through it slowly. So we have our learning goals are to know the difference between a vector and a scalar quantity. Find the magnitude of a vector in 2 dimensions given its endpoints. Magnitude means length or size. We're going to find out what a unit vector is. Use vector notation properly. This is a huge one, especially if you've taken physics. So there's a different way of using vector notation in vector algebra than there is in physics. So you got to kind of get used to that communication aspect. It's really important. And adding 2 vectors, we're going to start that today and work on it again tomorrow morning, and then apply it tomorrow afternoon. And that 3 lessons is going to be our whole unit on geometric vectors. And then when I see you next, maybe back at school, I'm really hoping, we'll start algebraic vectors. All right, so starting off, there's 2 types of quantities. Vector quantities have a magnitude and a direction. So a size and a direction. So these are all examples of vector quantities: 50 kilometers east, 100 newtons down, 20 meters per second, that should be a degree sign, north 40 degrees east. And scalar quantities have magnitude only. So just a size, but not a direction associated with it. So like 75 kilograms, 30 centimeters, that should be a degree as well, 38 degrees Celsius. So what is a vector? In math, it's a mathematical object that represents a physical property. A vector is represented by an arrow, or another word is a directed line segment. The length of the arrow represents the magnitude. And you can do scale diagrams for your vectors, but we're not going to do that in this course. We're just going to do representative diagrams. And then the direction of the arrow represents the direction. And again, you could use a protractor and everything, but we're not going to do that. We're just going to use representative diagrams. And so here's a typical vector. Where it starts is called its tail, or its starting point. And where the arrow is, that's called its tip or its end point. So notation, a vector can be denoted by 1 lowercase letter with an arrow over top. So I could call this vector, so that's a little lowercase u with an arrow over top. And I tend to do just the one-sided arrow. You can do this as well. Obviously, a lot of mathematicians do this just because it's quicker, okay? Or a vector can be described as starting at point A. So you'd think of this point A being on a Cartesian plane, for instance, and ending at point B also being another spot on the XY axis. And we call this vector capital A, capital B, vector AB. So starts at point A, ends at point B. Okay, so 1 small letter or 2 capital letters, and each of these capital letters represents a point, the start point and the end point. Okay, and or a point-to-point vector, we call it. Scalar quantities, so just numbers, are denoted by lowercase letters. For example, X, Y, A, B, M and N are also used. So no arrow over top, that just means a number, like X could represent any number, 2, 3, pi, etc. The size or just magnitude of a vector. So just its length. All we care about is its length, not its direction. is denoted by absolute value bars. So when you see this, determine, this looks like the absolute value of vector AB, what you're saying inside your head is determine the magnitude of vector AB. So determine the magnitude of vector AB. So I made it easy for us to do that. So we can see vector AB starts at point A and ends at B. And we can make this right triangle in order to use the Pythagorean theorem to get the magnitude. We know that this side here is 1, 2, 3, 4, 5, 6 units long. And this side's 7 units long. So it's not hard to find how long AB is, but I want you to pay attention to how we write that. So we're going to show in our solution that we're finding the magnitude of vector AB. You might want to start by saying the magnitude of vector AB squared is equal to 6 squared plus 7 squared. And then to get the magnitude of vector AB, you know, we would square root both sides. And you can use your calculator. So the square root of 6 squared plus 7 squared is approximately 9. So we can have an exact answer first of all. So 6 squared plus 7 squared, oops, is 85. So square root of 85, that's exact. Or approximate with the dot over top is approximately 9.2. So that's the size. You could put units. And since it doesn't give you any, you can just write units. That's the length or magnitude only. Okay, so that absolute value bars means you're telling me just the length of the vector. Right, so that's notation. Two vectors are considered to be equal if they have exactly the same magnitude and direction. So draw and label two equal vectors. So we could do like really easy ones, like a vector that starts and then goes 2 squares to the right. We call that vector little u. Is going to be equal to, I could start anywhere else I want here and go 2 squares to the right. And I could say then that vector u is equal to vector v. But I can get a little harder too, and not just have a horizontal or a vertical vector. So I could start in a spot here and decide I'm going to go down 3 and left 2, for instance. And so this is going to be my tail and this is going to be my tip. And maybe I'll use a point-to-point vector for this one, so different notation. So this is point A and this is point B. And if I want to draw an equal vector, I would start anywhere else. You can decide. I'll have this be my starting point and I'll call it C. And then from C, I'm going to do the same thing, go down 3 and left 2. And call that point D. And that's also going to give me a pair of equal vectors. And I'm using the different notation here. So vector AB is equal to vector CD. Okay, so equal vectors have exactly the same magnitude and direction. So they're the same length and they also have the exact same direction. So two vectors are considered to be opposite if they have the same magnitude but opposite directions. So again, this is kind of just like definitions, same magnitude, opposite directions. And then on the next page, we'll look at drawing two opposite vectors. So I can do the easy way again, or I could do like, I'll do vertical and vertical this time for my easy examples. So I could go up 3 and call that vector u, and then somewhere else down 3 and call that vector v. Now those are opposite vectors, but I can't say that u equals v because they're opposite. Who knows what I could say about u with an equal sign and v? Anyone?
U equals negative v?
Yes, u equals negative v. So same magnitude, opposite direction. So those are two opposite vectors. And then I could do the point-to-point ones. So I could have A starting here and go over 4 and up 1, say. 1, 2, 3, 4, and up 1. So there's AB. And then I can do the opposite of that. So instead of going from my starting point, I'll put here, instead of going right 4 and up 1, I can go left 4 and down 1 for my end point. And I can say that vector AB is equal to vector, negative vector CD. Or because it's a point-to-point vector, is it okay for me to say that vector AB is equal to vector DC? Does that make sense? So if I flip the tip and the tail, they would be equal vectors. Any questions so far? Just a lot of definition stuff. Introduction stuff here. Okay, vectors are parallel if they have the same direction or opposite directions. Okay, parallel vectors that have different magnitudes, so they have different lengths. Parallel vectors that have different magnitudes or lengths are called scalar multiples. So scalar multiples is the math word for being parallel but having different lengths. Same direction or opposite direction, so parallel but different lengths. And we say they're scalar multiples of each other. So look at the graph. So here I've drawn vector u and vector v. Look at the graph and complete the mathematical statement. So what number would go in here to make this a statement true? Vector u is equal to some number times vector v. What do you think that number would be and why?
Two?
Close?
-2?
Negative 2?
Yeah.
Okay, so if you look at vector u, it's going down 1, 2, 3, 4, 5, 6, and to the right 1, 2, 3, 4, 5, 6, 7, or sorry, to the left 8. So down 6 and left 8. And this one's going to the right 1, 2, 3, 4, and up 1, 2, 3. So they have opposite directions, so that's where the negative sign comes in. And this is kind of, you can think of it as 1, 2, 3, 4. Sorry, my bad. Use color here. 1, 2, 3, and then over 1, 2, 3, 4. And there's a vector v in length anyways. and then 1, 2, 3, 1, 2, 3, 4. So its magnitude is 2 vector v's long, but it's in the opposite direction. So vector u is equal to -2 times vector v. And because we can put a number in here, that means that, therefore, u and v are scalar multiples of each other. So if you can put a number in there, then that means the two vectors are scalar multiples of each other, which means they're parallel vectors. They have the exact same direction. Okay, and then that's what this says in math speak here. If vector u is equal to some number, some scalar number, times vector v, where k is any real number, then u and v are scalar multiples of each other, which means they're parallel vectors. So it's kind of like math speak, but really all we're saying here is that if you can put some number in here that makes sense, then the two vectors are parallel to each other. That's what scalar multiples means. So a unit vector always has a magnitude of 1. So that's very important. Always has a magnitude of 1 unit. A unit vector is denoted by a lowercase letter with a hat on top. So if this is vector v here, then we call this v hat. So how you say it is v hat. V hat is going to have the exact same direction as vector v, but it's only going to be 1 unit long. So I could draw v hat would be like this. So exactly the same direction, but only 1 unit long. And I can see that vector v is the same as 5v hat. Does that make sense? Vector v is 5 v hats. Or is it 6? 1, 2, 3, 4, 5. It's 6 v hats, my bad. Because it's 6 units long. 1, 2, 3, 4, 5, 6 units long, and 1 unit is a v hat. Okay, so it's okay to say that vector v is 6 times vector v hat, 6 v hats. Okay, so now we're going to get a little bit trickier here. So express vectors b and c as scalar multiples of a. So you're given a here, which is over 1 and up 2. And we want to know what b is in terms of a and what c is in terms of a. So there should be some number you can fill in for each of these. See if you can figure out what the number is. So if I was doing this, I know this a is 1 and 2. So I'm going to go. So that's 1, 2, 3, 4, 5 times as long and in the opposite direction. So b would be -5 vector a's. And vector c is 3 times as long, but the same direction. So it's 3 vector a's. And you can see just by looking at the diagram that a, b, and c are scalar multiples of each other, and they're all parallel to each other. Okay, so express a, b, and c in terms of vector a hat. So definition of a unit vector. A hat, so any unit vector actually, you can always find the unit vector by taking the vector and dividing it by its magnitude. So you can think of this as the definition of a unit vector or the formula for a unit vector. So anytime you need to find a unit vector, you take the vector and divide it by its magnitude. So we're actually able, from our diagram, to find the magnitude of vector A. Because we know it, we can make a right triangle where this side's 1 and this side's 2. So the magnitude of vector A squared by the Pythagorean theorem is going to be 1 squared plus 2 squared. So that the magnitude of vector A is, I'm going to keep this exact, the square root of 5. And then following this definition, that would mean that vector A hat is vector A divided by the square root of 5. Oh, I don't need the magnitude bars around the square root of 5. So vector A hat is vector A divided by the square root of 5. A hat, sorry, vector A hat. And let me draw vector A hat here. I think it would be about, so root 5 is how long it actually is, which is 2.23. So it's going to be less than half as long. I'm just going to kind of guesstimate here. I'm going to go over it in green here, put an arrow. So there's my A hat, same direction, but only 1 unit in length. Kind of guesstimating there, but giving you an idea of what it would look like. So what the question really wants us to do is to write vector A, B, and C in terms of vector A hat. So first, let's think about vector A here. Well, we've got this. We know that vector A hat is equal to vector A divided by the square root of 5. So if I want to represent vector A in terms of A hat, I can just, I put the absolute value bars. Oh no, I've got them in my brain over root 5. If I want to get vector A by itself, I can just multiply both sides by root 5. And then I'll have vector A in terms of vector A hat. So vector A is actually root 5 A hats, which is about 2.23 times an A hat. And that's the hardest one. B and C are really easy because we already have them in terms of vector A. So from up here, we know that vector B is -5 vector A's, but we just found out that a vector A is root 5 A hats. So I can replace vector A with root 5 A hat so that vector B is -5 times the root of 5 A hat. And -5 times root 5 is about -11.2. So it's about -11.2 A hats. And then same thing for expressing vector C in terms of A hat. We know from above that vector C is 3 vector A's. And we know that a vector A is root 5 A hats. So vector C is actually 3 root 5 A hats. So that's probably the most challenging thing we've done so far. And again, this negative 5 root 5, that we said that was about negative 11.2, would mean there was about negative 11.2 of these little A hats that make up vector B. Okay? That's all that that's saying. So that's kind of how a unit vector definition fits in so far. First part of our lesson is really just definitions that we need to know for the unit. The angle between two vectors is defined to be the angle between 0 and 180 degrees formed when the vectors are placed tail to tail. Okay, so that tail to tail part is really important here. So if you're ever told the angle between two vectors in a question, it means the angle between them when they're tail to tail. So determine the angle between each pair of vectors. Well, this one they're already given tail to tail, so usually we use theta to be the angle between two vectors. So in this case, theta is 55 degrees. Here you can see that they are not arranged tail to tail. So we would have to move one of them. I'll move this one so that I've moved this vector over here. So now we can see these two vectors are tail to tail now, which means this would be the angle between them, and it would be 180 minus 130, which is 50 degrees. Similarly to this one, they're not tail to tail, but I can just move this one so that its tail instead of starting here, starts here. And then the angle between them will be 180 minus 125, which is 55 degrees. So that's just another definition that's important to know, is that when you're given the angle between two vectors, it's the angle between them when they're tail to tail. Any questions? Okay. The zero vector is denoted by 0 with a vector arrow over top. It has a magnitude of 0 and its direction is not defined, and it can be thought of as a point. So if you think of just a specific point on a graph, how long is it? Well, it's 0 long because it's just a point in space, and because it doesn't have any length, it doesn't make sense for it to have a direction. And that's why you can't use a capital letter as a vector, okay, because it represents a point. You have to use a small letter or a point-to-point vector. 2 points, a start and an end. All right, so question 8 is a little bit of a application of the stuff we've been talking about. So A, B, C, D, E, F is a regular hexagon. So given that regular hexagon there and the vectors that are drawn within it, or the lines drawn within it, give an example of each of the following. So use point-to-point vectors. Give me an example of 2 equal vectors from that diagram. Somebody unmute yourself and I'll draw them on the diagram and then we'll write them out. 2 equal vectors. Remember, it's a right. What'd you say?
FB and EC.
Nice. FB. FB. So look how with my arrow, I start at F, I end at B, and EC. I start at E, I end at C. So FB equals EC. Okay, how about 2 opposite vectors?
DC equals AF.
BC.
DC.
Sorry?
I guess you could do it that way as well.
Okay, if I use BC, what's opposite?
EF.
EF? Yep. So BC is equal to negative EF. But those are opposite vectors. Nice. What about parallel vectors that have different magnitudes? They're parallel, but their magnitudes are different.
EB and DC.
Yep, EB and DC. Okay, so they're scalar multiples of each other. So I can't say they're equal. So EB and DC are parallel. So they have the same direction, but they have different magnitudes. And how about vectors that are the same magnitude, but they're not parallel?
I have a question.
Yep,
For B,
yep.
would it be negative? Because like it wouldn't be negative, right? Because you're going from B to C and then EF. They're opposite directions already. Don't you only
Right.
make it negative when they're in the same direction?
Okay, so Hannah, I want to use an equality here. I want to say they're equal. So if I'm just saying what are two opposite vectors, you're right. I would just say BC and EF are opposite. Does that make sense?
Yeah.
But if I want to make a statement of equality, if I want to say somehow they're equal, it's BC is equal to negative EF. But this is
Okay,
fine. I could
thank
just
you.
say BC and EF are opposite vectors. That's fine because that's really what the question's asking, right? Okay, so what about for D? Vectors that are equal in magnitude, so they have the same length, but they're not parallel. Could I say like vector AB and vector AF? Because it's a regular hexagon, they have the same length, but they're definitely not parallel. Does that make sense to everybody? And a nice way of saying that is we can use magnitude notation. So we can say the magnitude of vector AB is equal to the magnitude of vector AF. So I can use those absolute value bars and state an equality there, even though they're not the same direction because I'm just talking about their lengths are the same when I write that down. Okay, so that's kind of our intro, like just some notation and things to be aware of. Now we're going to start with adding, and we'll continue. Tomorrow morning, we're going to do adding and subtracting. But we're just going to focus on adding and making really nice vector diagrams and getting ourselves back into thinking about trig a bit. Okay, so adding geometric vectors. So when adding geometric vectors, they are added tip to tail. The vector sum is called the resultant and usually requires trigonometry to find its magnitude, size, and direction. So here's our first example. A boat sails 40 kilometers on a heading of north 41 degrees east, and then tacks and sails another 30 kilometers east before arriving at an island. So part A is to draw a vector diagram outlining the situation described above, including the resultant displacement, which is denoted by the D vector. So 1A, we're just going to draw our vector diagram. So I always start off with a compass. I try to kind of map out in my head. So I'm going to be going northeast and then east. So I'm going to put my compass down here using a ruler. And then always like this is north, east, south, and west. And then I'm going to look at my magnitudes here. I'm not using a scale diagram by any means, but I do kind of want it to make sense. So I see that my first vector is going to be longer than my second one. And I'm not going to use a protractor either. But so north 41 degrees east means I start off going north and then I veer off 41 degrees towards east. And one thing that everybody should know is that between north and east is 90 degrees, right? Because that's a 90-degree angle there. And halfway between north and east, northeast would be 45 degrees. So it's going to be a little less than halfway, which is hard to ballpark, but do your best. And then I'm going to start from here, try to be a little less than halfway. Just a representative diagram, and make it a certain length, and then put an arrow on the end. And then I'm going to label it with a vector. Okay, so a vector has a magnitude and direction. So this vector I've just drawn is 40 kilometers, and then put the direction in square brackets. So the direction is north, 41 degrees east, and then closing bracket, square bracket. So directions always go in square brackets. And that also means that this angle in here between north and the vector is 41 degrees, which is probably important to put in your diagram as well. It's probably getting really small for you to read there. I'll try to make it bigger.
Do we have to draw the compass, or is that just something you do?
You don't have to. It does help you in finding angles, but if you're just really good at seeing everything in your head, as long as you label all the vectors and the angles that you're supposed to, then you're fine, okay?
Okay, thanks.
You're welcome. All right, so the next one. So now once I get to here, it says that I tack and sail 30 kilometers east. So east we know is this way, and it's going to be shorter. So there's my next vector, and I'm labeling that 30 kilometers east. So there's my second vector. Now I'm going to draw my displacement vector. So when you add vectors, the sum of the vectors is always from the tail of the first vector, so it's going to start there, to the tip of the second vector. So I'm going to draw in my resultant. It's from the tail of the first to the tip of the second. And it's got to have an arrow, so really make sure that you either use a different color or you really make sure that you show that arrow there. In a vector sum, you've got the two tips meeting here. And then this vector, it tells us to call it vector D. So I've got a vector symbol above my little D there. And there's my vector diagram. So A says draw a vector diagram outlining the situation described above, including the resultant displacement D. So usually a vector diagram is out of at least 3 marks for each vector you've drawn and labeled nicely. So part B says determine the displacement D of the boat. So, and then it has a little star here. Displacement is a vector quantity. So you're supposed to be able to know that just because they have D with a vector and arrow above, that you need to give both a magnitude and a direction. So how far is it, and in what direction is it? Determine the displacement D of the boat. So that means where is it according to where it started. So it's so many kilometers away from the start in such a direction from the start. We have to find both of those. So we've got these two sides here. We also have this angle. Does anyone know or want to describe how to get that angle there?
Is it cosine law?
Yes, we can use the cosine law, but does anyone know how to get this angle between these two vectors? That's what we need in order to use the cosine law.
You could do like a Z pattern with the north axis.
Right, so here's north, to south. So that means this angle here, which we said was 41, is going to be at 41 is also going to fit in there. And then this is going from south to straight east here. So that's 90 degrees. So this total angle in here is going to be 90 plus 41, which is 131 degrees. Does everybody see that? So we've got a Z pattern. I'll try to draw it in here. Here's my Z. So from straight north along this vector to straight south, since north and south are parallel, that means this angle, which is 41, is the same as this angle here. And then this angle is a 90-degree angle. So 90 plus 41 is the 131. All right, so writing it down is the important thing. So we're using the cosine law, yes, but we're also using vector notation. So we're saying that we're finding the magnitude of vector D, and I always write the squared there because that's how I use the cosine law. So the magnitude of this vector squared is equal to 40 squared. So the magnitude of this vector squared plus the magnitude of this vector squared minus 2 times, so again, cosine law, I'll just write it up here as a refresher if you forget it. So a squared equals b squared plus c squared minus 2bc times the cosine of angle A. That's the cosine law. So the magnitude of vector D squared is equal to 40 squared plus 30 squared minus 2 times 40 times 30 times the cosine of the angle across from vector D, or in between the two sides, 131 degrees. So make sure your calculator's in degrees. You should be able to go straight to the answer. So basically you're square rooting both sides here. So when I type mine in, I'm going to go 40 squared plus 30 squared minus 2 times 40 times 30 times the cosine of 131 degrees. And I see I've got 4,074.54167 on my calculator. That's the magnitude of D squared, so I have to square root that. So on my calculator, I go second square root of the answer, and I get approximately 63.8, and the units are kilometers. So notice my vector form here. I've got the magnitude of the vector is 63. Someone's got their microphone still on, guys. Magnitude of vector D is approximately 63.8 kilometers. All right, so is anyone having trouble getting that on their calculator? Everybody's okay? All right, so the next thing we have to do is we have to give a direction. So the direction we're going to have to give is going to be in terms of north, south, east, and west. So if I know this angle in here, which I'm going to call theta, then I can, if I want, I can add theta and 41, and I can say north that many degrees towards east. Or I can do east so many degrees towards north if I want to subtract from 90. There's a couple ways to do it, but this angle in here is the one that I need. So to find that angle, I'm going to use the sine law. So again, if you forget the sine law, if you're finding an angle, it's sine of an angle over the length of its opposite side is equal to sine of an angle over the length of its opposite side. If you're finding an angle, if you're finding a side, you want to have the sides on top and the angles on the bottom. It's just a proportion. So I want to find an angle which I'm calling theta. So I'm going to start with the angle on top. So sine of angle theta over the length of its opposite side, which is 30, is equal to the sine of the angle I know, which is 131 degrees, over the length of its side, which we just found to be 63.8. But if I want to be careful, I can keep an extra decimal place. Which I erased from my calculator. So 63.83. And then I want to find theta. So the first thing I'm going to do is multiply both sides by 30. So that gives me the sine of theta. And then to get angle theta by itself, you have to do something called sine inverse. So angle theta is going to be the sine inverse of 30 times the sine of 131 degrees over 63.83. So on your calculator, you're either going to do 30 times sine 131 divided by 63.83 and then hit shift sign or second sign, or your calculator like mine, you'll have to hit shift sign first and it opens up a bracket for you, or you open up a bracket. 30 times the sine of 131 bracket divided by 63.83, and you get approximately 21 degrees. And always, unless it says otherwise, round your angles to the nearest degree. All right, so that's my next question. Can everyone get 21 degrees on their calculator? And in grade 12, it is okay to go straight from writing down the sine law with the numbers filled in to the answer. Okay, you don't have to show all these in-between steps that we showed in grade 10 and 11. If you're just confident with looking at this and being able to type in, okay, I know it's going to be the sine inverse of 30 times sine 131 over 63.83. If it helps you to write in the middle steps, by all means do that, but you don't have to. Everybody okay getting the 21 degrees? So the most common mistake people make is they then write that the direction is 21 degrees, but that's not true. So vector D, it's approximately, so you need that dot there, 60. So the magnitude first, 63.8 kilometers, and then our direction goes in square brackets. And I'm going to do the one where I'm starting at north. And so this whole angle here, if I'm telling the person where I am compared to where I started, it's going to be 41 degrees plus 21 degrees, or 62 degrees towards the east. So B, determine the displacement D of the boat. That is the displacement D of the boat. You can just put a therefore in front, and that's your answer to B. So this is all my work for B, starting up here, I guess, and that's my final answer. Any questions about that one? Can you guys hear me? Just want to make sure.
Yep.
Yep, okay, so we're good on that one? Okay, so we're gonna go to another one now. Okay, so this one, instead of having like a context, like a boat, we're just given vectors. So given that the magnitude of vector A is 5 and the magnitude of vector B is 3, determine the magnitude of vector A plus B. Include a labeled vector diagram with your solution. So you're shown the vectors tail to tail, but you're asked for the magnitude of the sum, which makes our work a little easier. But we also need that labeled vector diagram, which is really important with our solution. So we know that we don't add vectors tail to tail, we add them tip to tail. So we have to move either vector A and put it at the tip of vector B, or move vector B and put it at the tip of vector A. I like to always keep my horizontal ones. That's just how I am. So I always move my angled ones, but some people are opposite of me and it's totally fine. So I'm going to move vector B. So I want to make it look like it's on the same angle and it's the same length. So I'm just moving vector B over here so that it's at the tip of vector A. Because if I'm adding two vectors, I add them tip to tail. And then I'm going to draw in from the tail of vector A to the tip of vector B is going to be vector A plus B. Make sure I have my nice arrow there. And then this is vector A plus B. And the orange one I just drew, it's a physical vector. It's got a magnitude and direction. It doesn't matter that they're just asking me to calculate the magnitude. In the vector diagram, I don't have absolute value bars around that because it's a vector. So all three of my sides are labeled. And they want me to find the magnitude of vector A plus B. So given in the question, I know the magnitude of vector A, so I know the length of that side, which is great. And they also gave me the magnitude of vector B, so I know the length of this side. Even though it doesn't look to scale, does it? I should have had them the other way around. It's okay. So I know two sides, and I've got this triangle here. Is there a way for me to know this angle between the two sides? Anyone? If these are parallel, does that help?
You could say imaginarily extend your A vector a little bit with like a dotted line, and you'd have 37 degrees there.
Yes.
And then you'd
So
form a 180. You could subtract what at 37 from 180 degrees.
For sure, John, you could totally do that. The other thing is that this forms the PLTC pattern so that these two angles add up to 180. But in the end, you're going to do the exact same thing and do 180 minus 37 degrees to give you the angle between the two vectors, which is 143 degrees. Okay, so this angle plus this angle have to be 180, or as John said, I could extend this like in my mind and know that that angle would be 37 since these are parallel. And then it's a straight angle, so 180 minus 37 gives you 143. All right, so now I have to find the magnitude of vector A plus B. So I can use the cosine law again because I have the side angle side. So the magnitude, this time I'm going to write it of vector A plus B squared. Okay, so I don't want to see just like the formula. This is like some people just use this formula and they don't use any vector notation at all when they're calculating. So be careful to use proper vector notation. So this says I'm finding the magnitude of vector A plus B squared. So that's going to be the length of side A squared, 5 squared, plus 3 squared, minus 2 times 5 times 3 times the cosine of the angle between the vectors, which is 143 degrees. And then I can go straight to my answer by using my calculator effectively. So I'm going to do the square root of 5 squared plus 3 squared minus 2 times 5 times 3 times the cosine of 143 degrees and that is approximately 7.6. And since it doesn't give us any units, you can just write units. And that's the answer. So given that the magnitude of vector A is 5 and the magnitude of vector B is 3, determine the magnitude of vector A plus B, which we did. Include a labeled vector diagram with your solution, which we did.
Do we have to say units?
Yes, I guess the answers in the back of the textbook will have units. In geometric vectors, once we get to algebraic vectors, we can use the units, okay? All right, and then our last example for today. Two vectors u and v have magnitudes of 5 and 8 respectively. If the angle between them is 32 degrees, find vector 2u plus v, include a labeled diagram with your solution, and state the direction in the form square brackets u so many degrees towards v. Okay, so I'm going to start off with, I always like to have one horizontal. So here's my vector u. And v, I'm going to draw them tail to tail first of all. U's smaller, and they're at 32 degrees to each other. U's a bit longer. So that's kind of like my initial diagram, with 32 degrees being in here. But now I want to draw vector 2u plus v. So vector 2u is going to be twice as long as vector u. So I'm just going to go right over top with my orange marker and make this twice as long as looking, like I'm not using a scale or measuring, I just want to make it look twice as long. So this orange vector is vector 2u. And then I want to add on vector v, so I have to add it on to the tip of vector 2u. So I want to make it look like it's parallel and the same length. And then I want to label it vector v. And then vector 2u plus v is going to start from the tail of vector 2u and go to the tip of vector v. And I want to make sure my arrow is at the tip of v here. And I want to label it 2u plus v. So that would be my vector, my labeled vector diagram with my solution. Okay, so some things that I need to know then before I go ahead and start finding the magnitude of vector 2u plus v and its direction. First of all, what's the magnitude? How long is vector 2u?
Ten units?
10 units?
Yep, 10 units, awesome. And we were given vector v, it was 8 units. So I know the magnitude of 2u and I know the magnitude of v. I need to know this angle then in here as well. And we can do the same thing as last time. So 180 minus 32. So that angle in there is going to be 180 minus 32. Which is 148. Made my diagram a little bit small here, but that's 148 degrees in there. So now that we've got everything we need to find the magnitude of 2u plus v. So then I'm going to start doing that. So the magnitude of vector 2u plus v squared is equal to, so the magnitude of 2u, 10 squared, plus the magnitude of v squared, 8 squared, minus 2 times the length of 2u times the length of v times the cosine of the angle between them. And then if I square root both sides, I get that the magnitude of 2u plus v is approximately. Okay, so square root of 10 squared plus 8 squared minus 2 times 10 times 8 times the cosine of 148, approximately 17.3 units. So there's the magnitude. To get the direction now, it says that once the direction, so starting off going in the direction of vector u, and then how far do you go towards vector v? So they do want this angle in here, which is theta. So the angle between vector 2u and vector 2u plus v is the angle they want us to find when they say express your angle in the direction of vector u so many degrees towards vector v. So I'm going to use the sine law, and I'm going to start with angle on top. So sine of theta over the length of the opposite side, which is 8, is equal to the sine of the angle I know, which is 148 degrees, divided by the length of its opposite side, which is 17.31, if I want to be more exact. That was the decimal in my calculator. And then if you can go straight to angle theta equals approximately, it's going to be, I'll write it over here, theta is going to be the sine inverse of 8 times the sine of 148 degrees over 17.31. And I got that angle to be approximately 14 degrees. And we didn't have to do any subtracting because the angle we found was the angle between vector u and 2u plus v, or the vector 2u and 2u plus v. So now I can go straight to my therefore statement. So therefore vector 2u plus v, so I don't have absolute value bars because I'm stating the whole vector now with magnitude and direction, is approximately 17.3 units. And my direction is in the direction of vector u, 14 degrees towards vector v.
Would we ever want to use like a unit vector there? In directions?
Yes, sometimes they'll ask you to do it in terms of unit vectors. I think we'll see an example of that tomorrow, John, I think. Any questions? So we looked at 3 examples of adding. There's a few examples today, or for practice questions, sorry, but tomorrow we're just going to do, the morning lesson is just going to be adding and subtracting vectors. And then the video recorded one is just going to be adding vectors, but applying it to forces. And then, as I said, that's it for geometric vectors. Okay, so I'm going to stop the recording and just talk to you for a minute, and then I'll let you go.